review lesson will be on the particle theory of light. You can find more information in your notes on quiz 2B, particle theory of light. Previously, on quiz 2A, we talked about the wave theory of light. What's mainly different about quiz 2B is the introduction of this idea, the concept of the photon, or viewing light as photons, a unit or quantum of light, a particle of electromagnetic radiation. So this idea of picturing light coming in packets of these little particles. This would be a blue photon, green photon, a red photon. Changes our perception of the way light works and helps us to describe some phenomena better than the wave theory of light might. So when we were speaking of the wave theory of light, we also had the wave equation for light, and this is very similar to the generic wave equation, which is just the velocity equals frequency times wavelength. The one difference being now is that we use c for the speed of light, which we know the speed of light in a vacuum is constant. That's 3 times 10 to the 8th meters per second. So this equation was from the previous quiz, and even though you won't have to use this for calculations this time, you should be familiar with it because it's going to come in handy with helping explain some other things. You do have to be able to use this to do what I was calling in class arrow math or arrow algebra. For example, we know in all of our situations, we know that c is a constant, the speed of light. It's going to be the same every time, so that'll stay constant, it won't go up or down. And then, there's basically just a couple of situations you have. For example, if frequency were to increase, if you're going to go from maybe a red light over to a bluish light, then frequency, we know the frequency will increase. And what we find out is if frequency increases, looking at this and just being aware, in order for frequency increases, in order for c to stay constant, that means, well, both sides have to stay constant. So for this side to be constant also, if frequency increases, wavelength has to go down, has to decrease. Whenever frequency increases, the wavelength of the photons has to decrease in order to keep the speed constant. Well, for Unit 2B, we're talking about particle theory of light. We have a new equation we're adding to our toolbox. This was from Max Planck, who was investigating black body radiation, and he determined that energy seems to come in packets, and he came up with the equation that we see here. And we know, once again, F is the frequency of the electromagnetic radiation or the photon, and then E is the energy of that single photon, and then H ends up being Planck's constant. We have the value of Planck's constant in our notes, and we use it in some of our warm-ups in class, but for the quiz, you do not have to know or memorize the value of Planck's constant. And as a matter of fact, on this quiz, quiz 2B, there will be no calculator problems to do on this quiz. But you will have to do, the arrow math algebra type problems. So let's go over a few examples of questions you might see on quiz 2B. So a question might be something like this: which photon has the highest energy? And I give you a photon with a frequency of 10 hertz and another photon with a frequency of 100,000 hertz. So we're talking about energy, so this is where you need to have the equation. The energy equals Planck's constant times the frequency. And now you would use this and these numbers, but you're not actually plugging in numbers or using a calculator, you're just using arrows to figure out what's going on. Remember, just view this as it's always two situations. We're moving, pick a direction, moving from the A to the B. So we're going from 10 hertz to 100,000 hertz. So let's see how this will work. Well, first of all, we know H is Planck's constant. So that's just going to be constant. It's not going to go up or down. And then we're moving from 10 hertz to 100,000 hertz. So what's happening is the frequency is changing. It is going from 10 to 100,000. So it's increasing, it's going up. So in other words, frequency will go up. Now, if I'm looking at this, I'm seeing if I take a constant number times a number that's getting bigger, this whole side of the equation will get bigger. And since they're equal, since both sides are equal, if this side of the equation gets bigger, this side of the equation has to get bigger. Therefore, energy has to increase. if we had to write this answer out, it would be something like, the answer would be the second photon has the highest energy of these two photons. By using Planck's equation for photon energy, we can see that as frequency increases, the energy has to increase also. Let's try another example. Here it's the same type of problem, which photon has the highest energy, but now I'm given the wavelength 10 meters and the wavelength of 100,000 meters. Well, this is a little more complicated because it involves wavelength, so we have to use our wave equation, and it also involves energy, so we're going to end up using both of these, the energy equation and the wave equation. And before I get started, let me mark my constants. I know the speed of light is going to be constant there, and Planck's constant is going to be constant. So now again, I'm moving from here to there. I'm going from 10 to 100,000 meters. So what I'm doing is I'm increasing the wavelength from 10 to 100,000 meters. So as I increase the wavelength, looking at this first equation, I can tell if wavelength goes up, to keep the speed constant, frequency has to go down. So I know frequency is going down. So I'll bring that over to here. I know frequency is going down. So as frequency goes down, this whole side of the equation goes down. And since this whole side goes down, energy has to go down. So again, as wavelength goes up, makes frequency and energy go down. So as I go from here to here, the energy went down. Therefore, which photon has the highest energy? The 10-meter wavelength photon has the highest energy, because if we go from 10 meters to 100,000 meters, the frequency and energy went down. So this one has the lowest energy. So here's the electromagnetic spectrum, and the visible light spectrum inside there. And we sort of have these two competing and coexisting views of light. Earlier we talked about light being a wave, and we saw how there's various pieces of evidence that light behaves like a wave, such as the fact that light refracts, light exhibits interference, and light also undergoes diffraction. But what we're seeing now is that we talked about black body radiation presenting evidence that energy comes in quantum or small bite-sized pieces, and what we're going to mostly focus on now is the photoelectric effect. So these are the sort of the basic pieces of evidence to support light as a particle or light as a wave. And together we sort of call this the wave-particle duality of light, because light, both of these explanations work for some things and not for others. So neither one of them's correct 100%, and neither one of them's incorrect. It depends on the situation as to which explanation works best. So let's try to focus on these two aspects. From our previous lessons, we would call the view that light is a wave is sort of the classic physics view of light. The classic physics view generally views light as a wave, and light's waves can add up with each other, or they can add up over time to make a wave of greater amplitude. So waves, think of it as if you have two waves together. When they add together, they make one bigger amplitude wave. Well, now what we have is also the modern physics view of light. And modern physics realizes that light can sometimes behave like particles or photons, especially at higher energy levels, higher frequency. These particles act as single entities and do not necessarily add together. So here I have several photons, and we can start picturing light maybe as being as particles or pieces. So what I want to show you is basically on this side, this would be light as a wave, classical physics. That was on our previous quiz, quiz 2A. Whereas on this side, this is more like the light as a particle or modern physics would be what we're focusing on for this quiz, quiz 2B. So let's see how these might compare. Where we really notice the differences between these two theories is when we look at something called the photoelectric effect. The photoelectric effect is the observation that many metals emit electrons when light shines upon them. So as I showed in class, this simulator that has, for example, this is sodium metal, it simulates sodium metal right here, and this is a light source. And right now it's on violet light, and you can change the intensity or the brightness of the light. And you can see it's when the light shines on there, these electrons, these little dots are supposed to be electrons that get ejected from that plate, move over to the other plate, and you get a current here. And we did various observations. So you can change the brightness of the light, okay, increase the brightness or lower the brightness, make it dimmer. You also can change the frequency of the light by changing the color. We can go up to blue, which is going to be a lower frequency, or green, even lower frequency. We can go down to even to ultraviolet, which is not visible, but it's even a higher frequency. And we did various observations with this. You'll notice how the speed of the electrons are changing in different times, and the current can change by manipulating these controls. So let's first. How would classic physics or the wave theory of light try to explain or predict what the photoelectric effect might do? So I'm going to see, here's the plate. It's kind of a curved plate like this, and that'll be our sodium plate. And so classical physics would sort of see the best way to think was maybe a magnifying glass, some kind of magnifying glass lens like this, and it might. Wave theory might picture these waves of light coming in like this into this magnifying glass, and the magnifying glass focuses these waves together like this, and essentially you end up with a really high intensity or a big amplitude wave that hits the plate like this, and then that would eject electrons. Now, modern physics, or the photon theory, instead of seeing this light as a wave, it would see these as individual photons of, for example, 395 nanometer photons hitting and striking the plate. And then when you change the intensity, what you're actually doing is you'd be increasing the number of photons that strike. And instead of, not necessarily the amplitude, but the amount. If I go down to a lower intensity, you're going to have fewer amount of photons striking. You still can change the color, so we could go to a different color of photons, and then so now you can get a better picture of with photon theory. It's even this individual particle striking, so it changes our predictions a little bit. So let's see, using modern physics, with the photoelectric effect, how would it explain the photoelectric effect? And so there's our plate again. All right, so the difference is now, instead of seeing it as a continuous stream of waves, it observes every single photon. Every single photon is a separate incident striking the plate. So here I'm going to use a red photon and a blue photon. Remember, the red photons have a bigger wavelength, and they actually have less energy. So what happens is the blue photon comes in and has a large amount of energy, and it can knock an electron out off the plate. And when a red photon comes in, it has not enough energy, so it cannot eject an electron. So the major difference is over here in classic physics, these waves can add up and add their energy together and sort of team up on an electron and eventually knock an electron out. But photon theory says no, each photon is separate and individually hits an electron. This blue one comes in, has enough energy, and knocks out an electron. The blue one comes in, has enough energy, knocks out an electron. Another blue one comes in, knocks out an electron. The red one comes in by itself, one red one hits the electron, can't knock it out. Another red one comes in, hits electron, can't knock it out. These red photons cannot gang up on one electron and eventually knock it out. So it's just each individual photon cannot knock out an electron. So let's see how this affects our predictions of the photoelectric effect. So I have three sort of scenarios or questions that we're going to analyze here using the two different theories to figure out what might you predict to happen. So first, over here, we'll do the classic theory each time. The classic theory, wave theory, says that should red light eject electrons from sodium? And classic theory predicts that yes, red light can eject electrons off of the metal plate, because since the waves add together, you could either, it should make sense, you could either use bright red light, which is really, really intense, and that should have enough energy to knock out an electron. Or if you have dim red light, then you just wait a long time. Just wait a while until the energy builds up and knocks an electron out. Kind of like when you're trying to start a fire, maybe trying to start a fire with a magnifying glass. The energy of a giant magnifying glass will add up and start a fire, or it'll take some time for a smaller one to start a fire. But yes, eventually red light should eject an electron. Now, the photon theory has a different conclusion. It would predict no. It predicts that the energy of a single red photon is too low to eject an electron. One photon comes in, one red photon comes in, it cannot knock out an electron. And it doesn't matter how many, how bright. If the light was really bright, it just means a lot of red photons will be hitting it, and a lot of red photons not knocking out, each one not knocking out electrons. So there would be no electrons being knocked out by a red light. What about how do we get faster electrons? So we know about if it can knock electrons out, but what about to create faster electrons? How might we do that? Well, if light was a wave, you would predict that you could just increase the intensity or the amplitude, the brightness of the light, and that would make faster electrons, because more energy from more intense, more amplitude should make it faster electrons. Or you can increase the frequency of light, because we know that higher frequency does have higher energy. But the photon theory makes a little bit different prediction. It realizes that only higher frequency of light can create faster electrons, not increasing the intensity. Because if we increase the intensity, what we find out is, again, more intense means more of these red, or more, let's say more green. If more green light's hitting the plate, then it just makes more medium speed electrons. It doesn't make faster electrons, it just makes more medium speed. So the intensity doesn't have anything to do with the speed of each electron, it just makes more electrons happen. And finally, how long does it take to start ejecting electrons? Well, classical theory predicts that if we're using waves, just like trying to start a fire, it takes some time to build up the energy to eject electrons. You would shine your light on the surface, and after a few moments at least, it would build up the energy and then finally eject the electrons. But photon theory, again, comes with a little bit different prediction. It realizes that electrons are ejected immediately as soon as the first photon strikes the sodium. And this makes sense if you think of each individual photon as acting on the plate. A red photon comes in, doesn't do anything right away. And then as soon as a blue photon comes in, boom, it ejects an electron. It doesn't have to wait for 30 or 40 or 50 of these photons to come in and affect one electron. One single photon affects one electron immediately. You have a chart similar to this in your notes, but it's really best to kind of use logic to figure out what's going on in the. And one way to kind of do this is just think about what actually happens versus what we thought would happen when we first made our basic common sense predictions. Most of these over here, using classical physics or wave theory in this case, are wrong. Like this one, this entire prediction is wrong. Over here, increasing intensity does not make faster electron. That part's incorrect, but this one part is correct because it has the same prediction as photon theory. And then this one down here is incorrect. So basically, we know that by seeing light as photons, that it completely explains the results that we get from the photoelectric effect, whereas seeing light as a wave has some problems with trying to explain the photoelectric effect. And that's why we spent so much time talking about the photoelectric effect today. It's one of the major pieces of evidence that help explain that light can be seen as a particle at times. So there you have it. Those should give you the basic information you need to do well on the quiz. One other thing you need to study and look at is review absorption and emission spectrums and the Bohr model of the hydrogen atom to see how emission absorption spectrums work.